I still see, but not many. And but once I start presenting, then I will see nothing.
See.
Okay. So then I'll stop presenting, and then I'll start again. All right. Due to some reasons, I see you, but not speaker. How to change it?
Just switch off your audio
from?
Yeah, from here. Like you have to switch off the audio on the left.
No. I can see Chinghao, but not the speaker.
Yeah, because Chinghao. Yeah, try to speak, Oleg.
Oleg, can you speak?
Yes, I'm ready.
I cannot see you. How to?
Give me 1 sec.
Just a moment. Because in my laptop, I can see. I believe I'm recording my laptop, right? So in my laptop, I can see only
the whole screen, I think, because you are now in the presenting mode.
I'm not in presenting mode. Why? Yeah, I should be.
No, it should be on presenting mode on that.
On that?
No, it's on presenting mode.
But that is the. Is it okay?
Yeah, that's okay. Yeah, that's already.
It's standard, right?
Yeah.
Okay. I cannot.
It depends. Only
depends
when
if you
he's
go
speaking.
screen, yeah.
When he's speaking, you will be showing.
Yeah. Ali, can you speak something?
Yes, I'm ready.
No. Yeah. Okay. Now it's okay. When
everything is fine.
You will be visible, and there are more people waiting in the room. Could you accept the room?
When is it?
In the room, they're asking to admit them. No, nobody.
No.
Nobody. Okay. It was it. Okay. Then I see. Okay. No.
I do mute.
No, I have no sound.
I should fix. There is the.
Alexander, microphone is switching off.
No, that one. I believe that one. I can hear from you. That is off. That is off. No, there. Here. I heard that. Here. Yeah.
So
Okay. Sorry for that. Some technical problems. So we start seminar. University of Zambia applied mathematics seminar. Our speaker today is Professor Limarchenko from Shevchenko National University. And Oleg, could you at the beginning present yourself a little bit, and just in a few words, and then please start your presentation. Okay. So I'm asking all participants, please mute your microphones, and if it's okay with you, also to switch off your camera, then the connection will be a little bit better. Thank you very much, and Oleg, the floor is yours.
Can I start? Can I start?
Yes, please. Yes,
Thank
please.
you.
Yes, yes.
Thank you. I would like to explain initially why this problem appeared. It was happened so that I participated many times in processing of some experiments connecting with appearance of bubbles due to sloshing. But studying this problem, we study also some modes, then sloshing was not manifested. So we studied some modes of motion which are just close to resonance regimes, modes. And because of this, I have some experience in experiment. But mostly I deal with problems which are connected with transient modes of motion of reservoir with liquid. Mostly we focus our attention on combined motion of the system, then influence of liquid on motion of the carrying body is sufficiently strong, considerable. And because of this, my first acquaintance with problems connected with sloshing and steady modes of sloshing showed me that I have some doubtful position, and some of these positions studying these articles, and I would like to share this information with you and explain what looks doubtful and what is possible to improve. If we analyze our general ideas, I can focus my attention to the following. First of all, is some peculiarities, strange things of the problem of steady sloshing in publication. And according to my opinion, it has a lot of internal contradiction. For analyzing them, it is necessary to analyze factors which are usually ignored in experimental studies and theoretical studies, analyze some theoretical premises, I mean general approaches which are used for studying this kind of processes, and to construct the generalized picture of the resonance, which is an attempt to explain all observed modes of motion altogether. I suppose that I succeeded to do this. If we analyze articles in this direction, in this way, we can find a lot of pictures which looks very strange. I mean figures in this. For example, I will show you and comment what figures from articles it is necessary to take into account. The first line is connected with figures which were obtained as an experiment. This was done by Chinese PhD student initially, and later he works as a professor. He started his work in London. And what is interesting, what is necessary to say, his articles give some detailed information, but frankly speaking, a part of this information was given in 2003 by Indian scientist N. Pell. There are two Pells, Indian scientists. This is N. I don't know his name, and his name is very long. It is difficult to pronounce it, you know, Indian names. What is necessary to say? You see that here, linear prediction, no, give us previous slide. Linear prediction of this mode of motion is resonance, but you see initially it develops approximately like linear mode, but later failed and begin to decrease. And you see it can be periodic. And these three figures show that there is a mode, the third picture, where for some time it looks as a steady mode. I mean the third picture. Next line first picture in the left, bottom left, is the result of Norwegian scientist Rognebakke. I took it from his doctor thesis, and surely it was in the articles. This result is very strange for me. I can comment it. Initially, reservoir was at rest, and after the first period, approximately to 20 seconds, there is a transient process. Next period, from 20 to 30, it looks like steady motion. And he noted that this is steady mode, steady state. But if it is steady state, it will continue forever because no active actions were applied. And unfortunately, I fortunately embrace it, new transient process. That is why it is not a steady state. And I would like to focus your attention that if you analyze the field of this figure, you see that it is not homogeneous. There are some like spots in this steady process. And later I will explain what are these spots. And this result look thoughtless. Why? Because it is not a steady process, because you see partially amplitude change. Later it stopped and a new mode appeared. So it is, how to say, a lucky case. Then they catch this mode and later it was disappeared. And the last one, the right bottom figure, is the result obtained by another Indian scientist, P. Pell. Pell also the same surname, but another name. And these results show new mode. Before coming to next page, I would like to underline the following. All of these authors said that they study resonance. But how it can be that resonance gives so different pictures, but nevertheless they insist it is resonance. So it is very strange to understand. Let's show next picture. Next result was obtained also by Rognebakke and his collaborators, but about 15 years later. And you see, they analyzed, surely you understand that if the article contains experimental result, not every time you can see sufficient supplementary information about details of this experiment. Here they gave information about changing of force of interaction of liquid and tank walls. And you see, in spite of studying steady process, this force of interaction change in time every time, and it is also participate in the process of modulation of oscillation. Next figure shows us the elevation of liquids, so disturbance of a free surface. And my opinion, it is very strange that authors, you see the line and they wrote steady amplitude. It seems to me that it is a very, very optimistic way to explain this result. Surely it is not a steady mode of motion. Maybe it tends to steady motion in some understanding or approximately steady motion. But I know such results after some time, it can again be transient process. So altogether, this process showed that we do not catch steady motion, but it is close to steady motions only sometimes. And it is necessary to understand why it was so, because it is necessary to believe these authors, and it is necessary to, how to say, maybe, to use the principle of presumption of innocence, that they did their work honestly, and in this way they get this result. But how to explain these contradictions? Because their result differs from each other, and at the same time, they produce very interesting investigations. And following the previously taken terminology, it is like a criminal investigation, how to find a way, how to fit all these results all together and explain them. Next slide will show you that it is necessary to focus our attention on several interesting items. First of all authors ignores the information that usually if experiment installation participate in a combined motion, real normal frequencies are not do not coincide with partial frequencies, because combined character of motion change this frequency. All this offer ignores this. Next, normal frequency also depends considerably because of different ways of fixing the carrying body, and it is possible that ratio of masses and way of fixing, then reservoir can produce angular motion or cannot produce, will affect the final result. And also, they use the concept that the body can produce the prescribed motion. Usually, they suppose that kinematically it is sinusoidal motion, and they are thinking, they were thinking, that they succeeded to find a way how to reach it. But some graphs shows that it is not so. And really, this motion differs from sinusoidal law. Therefore, sinusoidal law is not taken into account. Frequency is traveling and they ignore it. And some of these results, I mean graphs, also showed that pure resonance and pure steady motion is not reached. Therefore, we decided to study this problem in detail, analyzing some additional factors. If we know theoretical things, in cylindrical reservoir, to determine normal frequency, if this reservoir is in rest position, is at rest position, we can use the formula which is in the left upper corner. And because of this, we can believe that this is a frequency. But if this reservoir will participate in a combined motion, you must solve this determinant which is shown in the bottom. Surely the result will differ from the upper formula, and now we will show how it will be different. Next slide, please. You see the graph which show the dependence of ratio of mass or masses of reservoir and liquid, and you see this dependence is sufficiently strong in the vicinity of 1 unit. Why it is necessary to focus attention, namely in this interval? Because the most interesting structures are just of such type that mass of liquid exceed mass of reservoir, and therefore change of this ratio produce considerable change of frequency. And later I will show that even small change of frequency will give you another mode of motion. Next slide, please. The most interesting situation appears then we use pendulum suspension of the reservoir. Pendulum suspension is much more difficult in analysis because it is necessary to take into account rotational motion of liquid. New potential will appear, vector potential. instead of one scalar potential. And what is the main result in this problem? Look attentively at the figures. Initially, there are partial frequencies 255 and 414. 255 correspond, this particular case really, 255 correspond to frequency of pendulum suspension, 414 correspond to normal frequency of liquid in cylindrical reservoir with radius 1, height of filling 1. In this case, there is a theorem which states if this system participates in a combined motion, the larger frequency will increase, the smaller frequency will decrease. So new frequencies will be outside of the initial interval between these frequencies. And how it can work? Usually, we have reservoir of rotation, of revolution, and because of reservoir of revolution, we used to separate normal modes into two parts. One is axisymmetrical, which correspond to circular number m equal to 1, and another one, m equal to 0, is axisymmetrical, m equal to 2, to 3, and so on. And what is interesting, only axisymmetrical mode change considerably, another do not change. Therefore, using pendulum suspension promote changing of the order of these normal frequencies. And the last picture show that the frequency, which is 414, it was the first flow liquid. It became the third because another frequencies became smaller. So this change of order of frequencies will considerably affect, because resonant mostly take place for the lowest frequencies. And this fact is not taken into account for this kind of resonant at all. Next picture, please. So we propose, look at figures, please. Mostly these experiments and the theoretical investigation was done for translational motion. We propose to do inclination, combined mode of motion, and also there are different ways of parametric oscillation. One way of parametric oscillation is classical Faraday problem. Another is generalized Faraday problem. Then carrying body can produce translational motion in lateral direction. And the last one, then this motion can produce, this system can produce angular motion. By the way, for this system, angular motion is much more significant than translational motion. For example, if we study rocket motion, you cannot push rocket and change its position for 1 meter either left or right direction. But it is simple to imagine that you can change its orientation for 1 to degrees, and also 1 to grades. And also, if you analyze, for example, C pitching, the same. C pitching also will produce not displacement linear, but angular displacement. But at the same time, it is necessary to analyze what is the purpose of, how to say it, hunting for steady process. If we analyze rockets, usually this problem mostly is connected with space launching system. Rockets produced by Musk usually flies in active period, I mean the first stage of this rocket, about 150, 180 seconds or 75, 80 periods. The best Ukrainian rocket Zenit flies 180, 210 seconds or 90, 100 period. But theoretical results, which correspond to experiment of Norway group of investigators, show that steady process usually installed after 150 periods. You see, later then this rocket will fall down. And what is interesting at the same time, if rocket is flying, usually due to consumption of fuel, level of liquid decrease. It is the essence of this problem. And because of this, no steady process can be observed at all. And for example, if you transport liquid, for example, in ships, surely liquid will not decrease. But at the same time, for sea pitching, only angular motion will be significant. Next slide, please. And we decided to focus your attention on such a problem. What are factors which are usually ignored in theoretical studies of sloshing? First of all, this is the most potential, most significant factor. Investigators usually ignore normal frequencies and normal modes of oscillation at frequencies of not the first normal mode. What I mean, there are axisymmetrical, then other for circular number m equal 2 and other normal modes. They say that only normal mode number 1, m equal 1 circular number, is taken into account, and according to usual tradition of studying 1 degree of freedom system Duffing equation, they take into account frequencies, multiple frequencies, omega 2, omega 3, omega, that's all. Next, usual experiments show that if the system has several normal modes, usually experiment register waves which has higher steepness than the first normal mode. That is why it is necessary to take into account high frequency normal mode with number m equal to 1 to take into account this increasing steepness. Next, combined character of motion of the system reservoir liquid is not considered at all, but I showed you that it changed frequencies. If system has another frequency, result will be reliable. And as I told before, there are many other problems connected with angular motion, some other modes of motion, parametric oscillation, and so on. Combination angular motion is reached because suspension point can move and so on. All these factors are ignored. And finally, some authors try to use amplitude frequency characteristic for summarizing the result of this process. But there is a famous book written by Kauderer, Nonlinear Mechanics, where he said that if process is multi-frequential, in this way, amplitude frequency characteristic will not work properly, because mostly it is aimed at a system with 1 degree of freedoms. And therefore, it is necessary to attract another means for analyzing this system behavior. Next slide, please. If we study theoretical premises for this problem, it is necessary, first of all, to mention the so-called Fermi-Past-Ulam paradox. First of all, this paradox has particular result that periodicity is possible if such relation, sum of omega I and I, equal to 0. And I is integer numbers, but it can be that this number can be negative. It is a complicated combined mode. And simply, this means that multiple frequencies can promote periodicity, and rational only relation between normal frequencies. But I told you in advance, and formula which is here put here above the table show that usually frequency pi is proportional to number pi square proportional to number. That is why pi is proportional to the square root of I. And why amplitude frequency characteristic is very popular in literature for presentation of result. This happened because of the following. If you analyze elastic oscillation, for example, simple excitation, like extension of rods, frequency is also proportional to I. Duffing equation, 1 degree of freedom, is also possible to use this approach. Beam oscillation, frequency is proportional to I squared. What are the properties of this oscillation? The distance between frequencies is large. For example, for rods, 1 to 3. For beams, 1, 4, 9. But for sloshing, spectrum is compressed. 1, square root of 2, square root of 3, and so on. Spectrum this is compressed. And there was an interesting result obtained for not the same problem, but similar problem by professor from Moscow, Terkrikorov, who showed how these large frequencies, large frequency spectrum will affect, it will produce some solitary waves finally. And sloshing time by time, people show that sloshing can result in some solitary waves. So this square root is a distinctive specific feature of this problem. And it shows that this process will not be periodic. By the way, people wonder if you will take function sine x plus sine square root of 2x. One function is periodic, another is periodic. Their sum is not periodic. Why? Because they will never coincide. Never you will find a solution, then both these functions are zero, for example. So simply two simple function, but not periodic if they will be summed. And this result was theoretically for the first time obtained by me together with PhD student Gubskaya, and later in another way it was obtained and published by Honorata. So this result state similar as Fermi-Past-Ulam result, that the process of sloshing, if we study it from position of nonlinear theory, will not be periodic. Not steady even, but not periodic at all. So it is very interesting result, which is necessary to take into account. Next slide, please. Summarizing this, we can say that there are no common ideas to produce scenario of sloshing. Next. No strict periodicity, therefore no steady process, and no amplitude frequency characteristic in strict substantiation. Usual system behavior of a multi-frequency mode is multi-frequency, and therefore it is not possible to produce simple interpretation of all these results. Artificial elimination of normal frequencies and normal modes of other modes, except the first one, considerably reduces nonlinear properties. And I will show by example that secondary resonance is also considerable, but this resonance will not be taken into account by model which I used here. No strict manifestation of steady sloshing in experiment and numerical results, because usually it produces some vague positions. And the result is the following. It is not possible to produce strictly sinusoidal law for motion of the carrying body. And we succeeded to solve this problem from the point of view of theory of control and to find how to, what force it is necessary to apply to get this result. Next slide, please. Surely, I should tell you something about the general idea of the method which I used for solving this problem. Surely this method is rather complicated and large, but for the simple problem, then reservoir is immovable. It is possible to write famous equation in nonlinear statement, which consists of harmonic equation, which is the result of homogeneity requirement. Next, non-penetration condition and nonlinear kinematic boundary condition on a free surface, and then linear dynamical condition, which equate pressure on a free surface of liquid. The most successful result for analytical approaches during the recent period were obtained by variational approaches. Famous variational approach based on Bateman-Luke variational principle for the first time was developed by Miles, and later it was modified by Faltins and Lukovsky, and they use it until present time. But I suppose that there is a big lack of this approach. I can explain you why. If you produce variation of this functional with functional, Lagrange function is used here, pressure. If you produce this variation, you will get third line formula. And in this third line formula, what is the benefit of this advantage of this formula according to ideas of authors? All problem statement follows from this variational equation. Why? These integrals are taken on different surfaces or for different variations. For example, the first and the last one, they are taken for different variations, but on free surface. Another in the domain tau of liquid and on moist and tank walls. And I find here hidden problem. What is the problem? Look attentively, please. If kinematic boundary condition is analyzed on a free surface, we produce its minimization. Later, approximate method will use minimization of this problem, this equation, on a free surface in undisturbed position, S0, with variation delta xi, that is variation of liquid elevation. On this surface, if it is immovable surface, we can produce a system of independent and orthogonal normal functions, the so-called basic system of function. But the last integral is used on disturbed surface, excited surface. That is why, if initially these functions were not orthogonal, were orthogonal, later they will not become orthogonal. And because of this method produce artificial simplification of the expressions connected with artificial nonlinearities. And because of this method was used mostly for a small number of normal function, usually 5, not more. And in the case, they never use it for angular motion, but in the case of angular motion, the total number of equations will be 5n plus 6, where n is the number of normal functions, normal modes. If we use classical Hamilton-Ostrogradski variational principle, finally we will get every time n plus 6. 6 is the degrees of freedom of carrying body. And we can organize this procedure in such a way that minimization of kinematic boundary condition and dynamical boundary condition will be by the same technology. And this make it possible to solve the first problem for kinematic boundary condition analytically for arbitrary number of n. Next slide, please. And if we use decomposition into normal modes, C decompose and corresponding to it potential phi, and for angular motion, the so-called stock Zhukovsky potential, it is possible to find these dependencies bi, qi, vector qi, in analytical form for arbitrary number of these normal modes. And therefore, we can eliminate bi and only use amplitudes of elevation of liquid free surface. And in this way, we will get simpler form of equation. But the most advantageable thing is the potential of using computer technologies, because we have no auxiliary problems to solve. All equation here gives you formula in explicit way, and it is possible to use up to, it is not limited. We use 20-25 functions, but mostly we work with 12 functions for approximating liquid elevation. So potential of computer implementation is much higher. Next slide, please. And the system of equation is very specific. If A n is amplitude of liquid elevation according to normal modes, epsilon is parameters of translational motion, and alpha is parameters of rotational or inclination. In this way, we can use the system of ordinary differential equations for their determination. And the greater advantage of it is that with respect to the second derivatives of these unknown parameters, it is linear. After this, it is possible to solve this problem by simple Rubin-Yakuta approach. And so we do this for different problems. Next slide, please. And I would like to show you this result. And by the way, I forget to tell you that mostly other researchers, they study behavior of liquid in cylindrical reservoir, either circular cylinder or prismatic rectangular prisma. We studied for arbitrary shape of revolution. For example, here I place the result, one-sheeted hyperboloid. If we study resonant, where force is applied, force, not a kinematic prescribed motion, force is applied according to sinusoidal law, and the left column show results, then tank is light. It is 5 times lighter than liquid. The right-hand part show then tank is heavy. It is 5 times more hard, heavy in comparison with liquid. You see how elevation develops. And I put here in the bottom the specific result. I compress the figure which was in the left column 4 times, and you see this figure practically coincide as a result given by Regnebacher and later by Faltenson, and only some maybe spots or shadow in the bottom. So in this way, this compression hides the system of very interesting low, high frequency peaks that are in this law of dependence. but it is far from resonance, only half of frequency. Next slide, please. This one corresponds to 0.75, so three-quarters of frequency. And you see here, modulation is considerably manifested. By the way, this result is most popular. And again, if you compress it, I did not do this here, you will get the same result as it was shown by Ragnebacher. Next slide, please. Here, you practically see results which were obtained by Zhang, a Chinese scientist who was in London. You see, this is close to resonance effect. And by the way, you can see that this interval of frequencies is very sensitive because the first frequency 0.98, another 0.2. You see how considerably it changed if you change only for 2-3% of frequencies. And it is shown that all these processes are modulated, but the period of modulation near the resonant increased many times. Next result, please. Next slide. Next slide. No, previous. Next slide show what you will get if you analyze after resonance, so post-resonant frequency, 1.25. You can compare this result, the right corner, right bottom result. It practically coincides with result obtained by Indian scientist Pell. So this model showed you that only it is necessary to analyze what frequencies are the resonant at this time. And even small mistake in analyzing resonance produce either pre-resonant or post-resonant effect. And it is necessary to understand that near resonant frequency behavior of the system is very sensitive. And because of this, even changing the frequencies for 1-2% will change considerably the final result. And therefore, it is necessary to study carefully the process of changing frequencies. And it is not a simple linear problem. Why? Because combined character of motion produce here greater effect than many other effects which are usually taken into account if we vary, for example, shape of reservoir and so on. Next slide, please. Here we show result for halfly filled spherical reservoir. Reservoir is light, 1/5 part of liquid. And here we showed pre-resonant frequency, near resonant, but here you see 10% below resonant, 10% after resonant, and near resonant mode. What is necessary to say? If you analyze a piece of this graph, for example, for ratio of frequencies 0.9, you will see that there is a long interval, then process is like steady one, but it is occasionally only for a period, long period of modulation, it can appear, but later it will disappear. And also what is interesting, there is a result of Shao, Chinese scientists, who studied period of modulation. According to this result, it should be symmetric before and after point of resonance. And you can compare a result for 1.1 and 0.9. You see periods of the last and the second figures is approximately the same. But it is necessary to say that if you, for example, produce 0.8 and 1.2, it will be distorted greater. So this symmetry appear at some distance and later disappear. You see why it is disappear? 0.98 and 1.02. They are different. So it is occasional result, mostly imported from linear theory, but it is also very useful for analysis. Next slide, please. Now I would like to show you the result, how to analyze what force is necessary to produce pure sinusoidal law of motion. We use the following. Variational principle of Hamilton-Ostrogradski make it possible to get all forces of internal interaction between liquid, for example, and tank walls. The formula, analytical formula, what is the interaction between these components, is given in the upper part of this slide. Therefore, if we add this formula into control of law, into law of control, excuse me, we will get compensation of liquid mobility effect on tank walls. Therefore, we solve two problems. The first one, we produce action by harmonic force F, solid line on the first figure. And finally, we get solid line, which is not sinusoidal in the bottom figure. But if we take into account compensation of this liquid mobility, this corresponds to dashed line in the upper figure. Dashed line in the lower figure show you pure perfect sinusoidal law. But surely nobody used this law during organization of these experiments. And by the way, then I participate in processing of experiments. Sometimes we increase weight of reservoir platform even 10 times, but cannot get pure sinusoidal law because near resonance, liquid produce rather strong liquid response. So this hypothesis that our reservoir is moved according to prescribed sinusoidal law is very powerful, and it is not fulfilled at all. Next slide, please. Another result. I told you that mostly people who study resonant ignored oscillation on the frequencies which correspond to not the first axis antisymmetrical normal frequency. Here, for circular number m equal to, frequency is 545. If we shake our reservoir on moving suspension point at the point of its suspension with frequency 545, after some period, the resonance will install, but what is the specific kind of this resonance? This resonance will produce considerable inclination. It is the, this inclination corresponds, alpha is, how to say, black line here, and considerable elevation, but mostly this elevation will correspond to first normal mode. Namely, normal mode m equal to 2 will be excited not like here, 0.35, but only approximately 0.04. 0.05. But what is interesting, this internal secondary resonance actually open a specific channel, then energy can be pumped through this normal mode from suspension point to the first normal mode and to inclination angle. And actually you get resonance, but this frequency is excluded at all in this model. So it is dangerous to avoid these in models. Next slide, please. This figure show you parametric resonance. If you have parametric resonance, suspension point produce oscillation in vertical direction, and there are two normal frequencies. One correspond to pendulum, another correspond to liquid. Angular motion correspond to red line. Blue line correspond to sloshing. What is interesting? The upper figure show you Fourier analysis of oscillation. You see a mixture of frequencies, just a great set of frequencies we register, then we study this problem for different space loading problems. That is why even simple excitation of this motion will produce considerably complicated character of changing of frequencies in this system. Next slide, please. I am closing to finish. But you can see sometimes there are a lot of small movies about sloshing. And you can ask me question how it can happen that I installed that sloshing is impossible, but later you can see sloshing, steady sloshing in these movies. I can explain this. I told you in advance that usually the Reynolds number here is about 10,000, 50,000, 100,000 sometimes. But if you reduce the size of reservoir, or you use another liquid, for example, glycerin or something else similar, you can reduce the Reynolds number. So you increase the effect of viscosity. In this way, if we produce frequency analysis by Fourier decomposition of this system, you will get the upper right corner figure that you will have strong manifestation of the first blue graph, strong manifestation of the first normal frequency, and a very small manifestation of another one nonlinear effect, and it is 2 times larger. And you see after approximately 40 seconds, here the process may be 50. Here the process is like a steady motion. Really it is so because damping suppress all other modes of oscillation. But the same system, if you will analyze it after resonance you promote high frequency modes. In this way, you see steady motion is absent. This graph, red line, is not so simple, and a lot of different frequency will appear near the main one. So it is possible to adjust this system to show steady motion of liquid, but it is necessary to increase viscosity artificially. How it is possible to do? Either to use baffles, for example, or to use, as I told you, small reservoirs and more viscous liquids. Next slide, please. One of the most interesting experiment was shown. Next slide, please. Yes. I am restricted in time, yes?
It's last slide.
Probably.
Okay.
If I am restricted, shortly, only shortly. There is an effect of anti-resonance, and we catch it. Previous, please. We found the mode, then during 5 periods of oscillation, liquid is practically flat. No oscillation is manifested for some time. It is nonlinear effect. And next slide, only shortly. there was an accident connected with shuttle. What was the reason of accident? Combustion chamber was destroyed, and the integrity of it was violated, and the jet, I showed it in the right corner, the jet appeared, and this jet produced the following. Tangential part of the jet produced rotation of this launcher, and normal action produce the so-called circular Godograph force. It is written in the right upper corner. What is interesting? If liquid will not move in this way, the system, the tail of this rocket will move according to the dashed line. But if we succeeded to initiate liquid oscillation, this motion will be solid line. What is the result of this? If you do not, if like during this accident, if you do not promote liquid sloshing, in this way, tail of the rocket will change its position, orientation of the rocket will considerably change, and it can fall down even on the starting position. But if you push, for example, it occasionally by some means, in this way, sloshing will keep it into order. And in this way, this motion will be much better. It can go outside of this territory, and later it can be destroyed in the at a safe place. Summarizing all this together, unfortunately, this problem was studied by people who study it not deeply, according to my opinion, and they do not take into account two main ideas. One idea, that it is impossible to produce prescribed motion of reservoir, and they do not take combined character of this system motion, but near resonant, this combined character produce, and the system behavior produce very sensitive interval of changing of frequencies and manifestation of resonance. But changing of frequencies, they ignore it at all. And we produce a model, which is a theoretical model, which can put all these results in an order which explain mostly these effects. And I can make separate report connected to this model and some result which were obtained by it, because this model successfully enables solving this complicated problem. Thank you.
Thank you very much, Professor Limarchenko. We have okay.
Can you hear me?
Yes.
Yeah, you can hear me. Okay, so we have time for questions. Even we are behind 3 p.m., but if we can stay longer. Any questions? Any questions? Oleg, as I understand, your point is that sloshing as a flow and a motion of container, they should be considered all together, and this means that the sloshing is actually a problem of fluid structure interaction. Is it right? Oh, it disappeared.
If it was a question, I didn't understand it considerably.
Can you hear me?
If it is a question, I cannot understand it completely.
Is it right that the problem of sloshing should be considered as problem of fluid structure interaction?
Surely. Here, according to my opinion, taking into account of combined character of motion, change the essence of this problem considerably, because additional degrees of freedom appear, the first one, frequencies change, and because of this, all effects were displaced from their previous position and new ones appear.
Yeah. Okay. And then, how to account for motion of the container in that variational principle, say, because here it's there are no motion of container.
It is possible to take into account the motion of a container. It depends upon the way of its fixing. So, for example, you know that usually, for example, for rocket, there are several containers, oxygen and then fuel, and also there are degrees of freedom and the position of the mass center, because usually this tank produce rotational motion with respect to relative to mass center. And because of this, it is necessary to analyze this system on the whole. But even in the simple problem, then you use translational motion, frequencies can change, for example, for 10%. It is a tremendous, huge change of frequencies for analyzing really resonant or some other kind of motions. And this factor is ignored. Why ignored? Because the problem became more complicated, and it is necessary to improve previous approach, to study it carefully.
Okay, and one more question about the same slide, slide number 14. Can you see this slide? Alec, can you see slide?
Now, yes.
Okay. As I understand, in this slide, big S is the actual position of the free surface, and big S0 is the kind of cross section of the container. Is it right? What's the difference?
Here,
Big
the
S
problem is
S0.
Cross-section of the reservoir is S0. Yes,
Okay.
it is undisturbed surface.
Yes.
S is disturbed, so it is during excited motion.
Yes.
But here results were given for simply cylindrical case. In the case of not cylindrical, it will be much more complicated.
Yeah.
I know only the general idea, most maybe significant idea of this method. It is connected with processing kinematical boundary condition. And because of this, it is possible to solve this problem carefully.
Yes.
And the main thing here is that it is possible to find explicit form of solution of it, and later load this problem to computer.
Yeah, I understand. Okay. Indeed, it's only this can be done only for cylindrical containers.
Mostly people solve cylindrical, but we succeeded to solve hyperboidal reservoir, elliptic, parabolical, conic swirly, and so on, spherical.
The weighted part is changing in time as well.
Yes, it is possible to use arbitrary, but this result, this method have not good convergence if inclination of tank wall will be to the center. So if you put a lot of liquid to spherical reservoir, when a roof will work, we cannot solve this problem. Only if reservoir is filled not to the roof.
Yeah. And as I understand, the Luke principle is more problematic than Hamilton principle.
Yes, but it was suggested for the first time approximately in 1960, and it was suggested for ocean or sea waves, and its advantage was that all the problem follow from it, from this variational principle. But according to the Hamilton-Ostrogradsky variation principle, it is necessary to satisfy all kinematic boundary conditions in advance, and only dynamical boundary condition and equation of the carrying body will follow from it.
Okay.
But we succeeded to solve this problem. Why? Because we study also solubility condition, and the part of these requirements just fit solubility condition, and therefore no body use Bateman-Hughes variational principle without satisfying kinematical condition on moist and thin wall and equation Laplace equation in advance, because without it this problem is very difficult to solve. So actually they do not use the advantage.
Okay.
And kinematical condition is solved not properly according to this approach.
Yeah. Okay. Thank you. David, do you have a question?
Yes.
Okay.
So my question is, it's about the nonlinearity effects. So what is the, after that you've done the Fourier decomposition or eigenfunction decomposition, what is the order of the nonlinearity that you have? Do you have, let's say, three frequency, three eigenfunction interaction, or is it four eigenfunction interactions?
Yes. Usually, you know, probably that the most significant effects are manifested then you use third order of smallness until first order of smallness. Here we have an attempt, then we take into account even until fifth order of smallness, but no significant changes happen. Third order of smallness is sufficient for getting nonlinear effects, which are usually mentioned in experiments.
So it's three wave interaction?
Yes. Okay. And the main problem is the following. We used disturbed free surface and did decompose all expression that we get on disturbed free surface and projected it on undisturbed using Taylor formula, taking into account values until the third order of smallness. This is our approach.
I see. So you can estimate the time of the recurrence.
Yes.
Okay.
And it is possible to increase this accuracy, but nevertheless, we do not expect that something will appear considerably important.
Sure, because all the other modes are very fastly dissipated, maybe. So only the low modes. Okay.
Maybe.
Thank you.
Okay. Any other questions, please? Okay, not many questions. So everybody clear. Thank you very much, Professor Limarchenko, and in particular for this audience and our school. It's interesting and important presentation because we are doing fluid structure interaction and to enlarge our field to sloshing, which commonly considered as the hydrodynamic problem, but not problem of fluid structure interaction, is interesting for us. However, from that point of view, there are some papers. It's about that sloshing in large containers, so the LNG tank sloshing.
Yes.
And for that sloshing, some people account for interaction between this sloshing and motion of the vessel. So they consider that forces produced by sloshing to calculate the motion of the vessel more accurately.
Mhm.
Yeah, and also there is the there is the some application from another field, from naval field, say. And also I remember experiments by I'm not sure they actually experiments, but could be experiments on the paper by Mark Cooker and from our school, and could be Tom Bridge from Essex. They studied the so-called shallow water sloshing. So the kind of large, not large, but shallow container with the shallow water on it, and the motion in swinging like that. So, and they managed to produce the solitary waves, as far as I understand. Or actually, it's not. It's like shock waves or on the surface, and the shock waves, they come to the wall, side wall, and impact on it, on one wall, then impact on another, on opposite wall, and so on. So it was a very interesting interaction between sloshing and rigid motion of this container. So, but that is approximate, and as that application for vessels, this is the pure numerical. So it's a kind of CFD, everything there. So I understand that your approach is more theoretical, and
Yes.
it gives more insight into the problem. So that is the interesting. I noticed that some our participants I expected to attend, they didn't come. It could be just a different reason for that. But I hope we recorded your seminar well, and I'll inform them and make kind of summary about, very short summary of your presentation, asking them to pay attention and potentially to use in their study. So thank you very much.
Thank you too.
Anything else? No? Okay, no. Okay, then we close our seminar. And just to remind our participants that we have the one last seminar this semester next week, and it will be given by Serebrekov, also from Kyiv. So thank you very much, all participants, and we are closing our seminar. And thank you for our speaker for a very interesting presentation, shedding light, not shedding, shedding light on the classical problem, but giving the unusual key story. Thank you, and bye-bye.
Thank you too.
Bye-bye. Now I should close it.
On your laptop. Yes, to stop the recording.
Yeah. Okay, just a moment.
It is necessary to switch off slides.
Yes, looks like that. Yeah. Because I cannot stop recording. Oh no, it doesn't.
Oh, where?
It doesn't. It's doing. Yeah. No, I cannot do. I cannot stop it. Just leave.
Oh, no, that's a share.
Yeah. No, I should stop. Okay. No, it's here. Oh. Okay. Finally. Ooh.